This video is sponsored by Incogni. Howdy! This is the 6th video in a series of videos about Simplex, a solid rocket motor that I designed, built, and fired earlier this year. And this is the last video in the series before we fire this motor. We came up with the design, we made the propellant, we made a nozzle, we made a forward closure, and we made a test stand. And now it's time to hydrostatic test it, which means we're gonna bring this thing up to 1000 PSI, 69 bar, and see if it survives. So let's get started. Fire. Like I said in the last video now, we've got all of the parts for our motor made, and even better, we know that they fit together. The last step here is to perform a pressurization test, which is going to tell us a few things. Is the case able to hold chamber pressure? Do the O-rings on the nozzle seal? Do the O-rings on the forward closure seal? Do the O-rings on the head end ignition bolt seal? And finally, do those pressure transducer ports seal? There's a lot of seals in this motor, and we gotta make sure they all work. Here's the thing. With a motor like this, we're only expecting to go up to about 400 PSI. And even if we have a bad day, we're not expecting to go more than like 700. Our case bursting pressure is 1400 PSI. So we're not really worried about the case popping, we're worried about verifying all of these seals. We're doing this test mostly because me, the dude who has never built a rocket motor before, showed up ballin' out designing and machining 7 different seals that have to all work at 400 PSI. We call this specific type of test a hydrostatic test, and I'll tell you why. We're gonna take our little cross section here, remove the propellant, but keep the other parts, and then we're gonna plug the nozzle, fill the whole case with water, and start pressurizing it to see if it leaks. We do this with water because it greatly lowers the explosive potential from a test like this, and if it leaks, we can see the drips from the water much more clearly. So first up, we have to make a plug to go into the nozzle. There's a big hole in there, and the only reason this rocket motor isn't a bomb is because of that hole, so we gotta plug it. I hopped into Onshape and cooked up this little guy. I matched the converging angle of the plug to the converging angle of the nozzle, so we have a theoretically flat surface, but obviously those two surfaces aren't just gonna seal. So I decided to add an O-ring between the two faces. As the pressure increases inside the chamber, the force on the end of the plug will overcome the pressure on the side of the O-ring and squish the plug down harder. This should work, in theory. To make the plug, I took a 3-inch rod of aluminum 6061 stock material, and I chopped it down to size on the horizontal bandsaw. Then I got to work turning it down on the lathe. I started this process by drilling a 7/16 hole down the center of the part, which will let pressure pass through into the case. And this lets us tap a 1/4-inch NPT hole at the top where we can mount a quick disconnect fitting. Then I turned down the length of the part that fits through the nozzle, creating lots of yummy spaghetti along the way. I will admit that after boiling it for a little bit, this pasta was delicious. After turning down the center, I turned the taper to the exact same angle as the converging section of the nozzle, just like we designed. Then, finally to finish it off, I grabbed my aluminum polish and went to town. I'm telling you, polishing these parts after making them is my new favorite thing. It's important to take pride in your work, and even if your work isn't perfect, it's a lot easier to take pride in something that is shiny. Like I mentioned before, I tapped the hole at the end as 1/4-inch NPT, and I added a fitting. Having a quick connect fitting at the end of this thing is going to be crucial to how we set up this test, so let's keep moving on. Now, if we're really going to test like we fly, or I suppose in the case of a static fire, test like we test, we need to have an igniter inside this motor, right? Well, sort of. In the forward closure video, I talked about making one of these ignition bolts, and I've actually made a few of them. This one in particular intentionally never got coated with the ignition compound, but everything else about it is the exact same as the actual igniter, so it should tell us if this design is solid without having to make a perfectly good igniter soggy. Alright, and with that covered, we can get set up for this test. First, I installed the pressure transducers into the forward closure. I wrapped Teflon tape around each transducer before putting it into the tapped holes to help with sealing in pressure. I used a wrench to tighten down all 3 of the pressure transducers. Actually, wait a minute. Hold on. 1, 2... looks like I forgot to tighten down that 3rd one. I wonder if that'll be a problem down the road. Oh well, let's move on. Next, I loaded the high-temperature O-rings up with superlube and put them on the forward closure. Since we aren't using a liner during this test, I skipped that bottom O-ring, which is supposed to seal against the liner. Lastly, I loaded the HEI, or head and ignition bolt, without pyrogen and tightened it down. I carefully loaded this whole assembly into the motor and screwed down all of the radial bolts to hold it in place. Getting the clocking of this part right with all of these radial bolts was a little bit tricky, but like many things in rocketry, it just took patience and a little bit of swearing. Next up, I lubricated and placed the O-ring onto the nozzle plug, then placed the O-rings on the nozzle carrier, also with a generous amount of superlube. Then, crucially, I put the nozzle plug into the nozzle and I wrapped some tape around the end to keep it from falling out. I then loaded the nozzle into the case and screwed it down with all of those radial bolts. I also attached a valve to the quick disconnect to keep the plug from falling down into the motor. I brought the test stand outside for the hydrostatic test. Now, in an effort to make sure I got some experience with the stand, I staked it down at all four corners using these metal stays. This is a bit overkill, but it helped me get experience setting up and taking down the stand. I loaded the motor into the stand, threaded the cabling through the bottom, and hooked it all up to the stand electronics, then connected the pressurization hardware. Before the test, I covered all of the stand electronics in a few trash bags to protect them just in case. Then I started loading up the case with water. I put as much water in as I could and began pressurizing slightly to get the plug and its O-ring to seat. And it was around this point that I realized that the O-ring between the plug and the nozzle had been slipping out.
Oh, it blew out the O-ring.
There was like too much pressure on the side of the O-ring, so it would just like pop through the nozzle throat, and that's no good. That's not gonna seal. Luckily, I had a simple idea for a fix in mind, and all I'd have to do is take the nozzle out. This proved, and come here. This proved, and I don't want to exaggerate, this proved to be physically impossible to do by hand. In order to get this nozzle removed, I had to grab some metal rope at the hardware store along with my ratchet straps, drill 2 holes in the case at the upper end, as well as 2 holes just at the edge of the nozzle. I then tied the metal rope through each end of the motor, attached one end of the ratchet strap to a beam in my garage and the other to the wheel of my car, and only then was I able to remove the nozzle. With the nozzle removed, I tossed the plug onto the lathe and turned a little groove into the tapered section so that the O-ring had a flat surface to seal against. Then I could start the fun, easy, low effort, and very enjoyable task of relubricating the O-rings, reinstalling the plug, reinstalling the nozzle in the case, realigning the radial bolt holes, reinstalling the radial bolts, then bringing this motor out to the backyard, filling it with water, and repressurizing. Thankfully, this time the plug sealed perfectly against the nozzle, and we were able to get the motor up to about 550 psi, which is great, but it's not enough. The goal for this test was to go up to 1000 psi or 69 bar, and there were enough leaks somewhere that my pump just wasn't able to get that much pressure in there. Also, to be very clear in terms of safety, for all of these tests, although it's a hydrostatic test so it's fairly safe, I'm controlling all of this stuff from a separate room, so I've got access to the pump, relief valve, analog, and digital gauges to tell me how high the pressure is inside of the motor. I wrote a little piece of ground control software to display the thrust from the load cells, pressure from each transducer, and a few other metrics, and all of that stuff gets beamed from the test stand down to my computer via that 900 megahertz link. Anyway, it turned out the leak here was coming from 2 different places. The first and most concerning place was through the graphite of the nozzle. Graphite, as it turns out, is a somewhat porous material, so air can leak through the material itself. It's a super interesting fun fact, it's just like a lot less interesting when you're trying to use it as a sealing surface. The second leak here was coming from the forward closure. Does anyone want to take a guess as to where that leak was coming from?
Looks like I forgot to tighten down that third one. I wonder if that'll be a problem down the road. Oh well, let's move on.
You guessed it, turns out you can't just hand tighten NPT connections. The good news is that all of these things are very solvable problems, and the bad news is that solving them requires a full de-integration and reintegration of the rocket motor. Okay, here we go. I brought the motor inside, I removed the forward closure radial bolts, removed the nozzle radial bolts, I then attached a metal rope to both sides, a ratchet strap to my Tormach, and a ratchet strap to the garage pole to get the nozzle out. Then I did the same for the forward closure, and it was so stuck that it started dragging my 800-pound Tormach mill across the floor, so I set the whole thing up again, but this time I anchored to my car wheel, and this time it actually worked. Side note, I also bought a lifting scale to see how much force this was actually taking to extract. The nozzle came out at about 59 pounds of force, and the forward closure took about 38. I wouldn't expect these numbers to be super repeatable, but is interesting, so. Then I retightened the pressure transducers and covered the converging face of the graphite in about 385 pounds of super lube grease, hoping that it would seal the graphite well enough. I then re-lubricated the nozzle O-rings, reintegrated the nozzle into the case, realigned the holes, reinstalled the radial bolts, almost forgot the plug, so I re-lubricated that and reinstalled it. Then I re-lubricated the forward closure O-rings, reinstalled the forward closure, realigned the holes, reinstalled the radial bolts, and finally, for the third time, we were ready for a hydrostatic test. This time, I laid the motor on its side to make things a bit easier, and the test passed with flying colors. The nozzle plug seal worked perfectly, the graphite didn't leak at all, the pressure transducers fared super well, except for P-tap 2, which had like a steady leak at some of the higher pressure portions of the test, but were otherwise fine. I felt comfortable getting the internal pressure up to 1000 psi, but I didn't want to push the case to failure, so I didn't go further. One cool thing you can actually see as we pressurize and depressurize is that the nozzle plug moves in and out if we loop the video. This is caused by the RTV between the pieces of the nozzle squishing, as well as the O-ring for the nozzle plug squishing. Pretty cool to see. So with the test done, the only thing left to do here was deintegrate and then reintegrate again. I'm not going to show you that process. I'll save you the trouble of it. What I do want to do is end on the following note. Doing a space shot is incredibly difficult. It will be the hardest project that I do to date, for sure. One of the hardest parts of a project like this, in my opinion, is going to be listening to the data even when I hate the data. So when we run a test like this and a pressure transducer is only hand tightened, we pretty much know with certainty why this leak is happening. But the smart thing to do, and like the necessary thing to do for a space shot, is we have to go back, deintegrate, do the whole frustrating process, and then come out and do it again. We have to prove why we think things are happening, and like with something as expensive and high risk and complicated as a space shot, we can't go out and just send it, even though that's really fun sometimes. Anyway, on that note, that is the whole build process for Simplex. Apart from like polishing the case and painting, which we'll cover in the next video. But there's one more video to go in this series of videos. Thank you so much for watching all of this stuff as we put this motor together and as I figure out how to build motors like this. As I said, in the next video, we're gonna fire this motor, we're gonna look at the test data, we're gonna see how it does, and then we're gonna talk about next steps as we work toward this space shot. But before we do any of that, it is time to talk about today's sponsor. This video is sponsored by Incogni. It's 2023 and the amount of data that is collected about you online every year is only growing. Some of that data you're probably aware of, maybe your name or your age, but a lot of that data you probably aren't. There are these internet data brokers that collect and aggregate things about you, like your name, your age, but also things like your social security number, your browser history, your shopping habits, etc. Some of these companies you can reach out to directly and ask them to delete your data, but the sheer number of these companies that exist make that basically an impossible task, which is why Incogni exists. Incogni is a service that reaches out to these data brokers on your behalf to request removal of your data and deal with objections from the company when that process isn't so smooth. Incogni is also on the clock 24/7 to keep watch out for your information online and request removal automatically. It's not just like a one-time thing where they remove all your data, it's a constant service where you remain protected. The first 100 people who use this code at the link below will get 60% off of Incogni, and one more time, that link is down in the description below. Thanks so much to Incogni for sponsoring today's video, and thanks to you for watching. My name is Joe Barnard. May your skies be blue and your winds be low.